My name is Seongkook. This work is done during my postdoc at the University of Toronto, and I'm currently at the University of Virginia. And this work is done with Jaeyeon Lee and Daniel Wigdor, and I have to thank the textual labs for supporting this work. So we bend things, right? Things deform, and some things deform more, some less. And we feel what kind of material it is and how strong it is based on what we feel. And when we wring out wet clothes, we feel the resistance. We feel when it stops moving or deforming, and we know when to stop from what we feel. So we get so much information about what we are manipulating from all these deformation. But what about the virtual world? We can't feel any deformation, right? So we are losing all that information and also realism. Such deformation can be simulated using force feedback devices, and there are tremendous great work in this area. So researchers developed methods to render high fidelity force feedback, not only for one hand, but also for bimanual haptic operations. These methods use mechanical links to physically create strong and accurate force feedback, and they can simulate deformations varying stiffnesses. But it comes at a cost of its large size and weight, making it difficult to be carried around. And we propose a different approach. Instead of adding resistance to the controller, we use a haptic illusion to reduce the deformation resistance from a rigid device. So here, we use a single 6 degrees of freedom force torque sensor and a single vibrotactile actuator and 3D printed handles. This device could make the rigid stick to be felt like it is being stretched, bent, or twisted. I hope everyone here had a chance to try our device yesterday at the demo session. And I'd like to explain how it works. In fact, this is not the first work that uses vibration to create an illusion of deformation. Johan Kildau introduced the concept of creating deforming illusion using grain vibrations in his 2010 paper. And in his model, an object is tethered to a wall with a spring. So if a force is applied to the object, it recedes and it moves back to its original position if the force is removed. And when the object moves, friction between the object and the surface causes friction-induced grain vibrations. And by simulating these discrete grain vibrations, he showed that he could successfully create the illusion that the rigid surface is actually being pushed when it's rigid. And while this method was originally tested with a stylus, it is also shown that the friction grain method could be used for two-finger squeezing. So, what are other deformations, like bending, stretching, or twisting? And here's a video of a sponge that makes crunching sound and vibrations as you deform it. Hopefully, I can make it a little bit louder. And we simulate these vibrations caused by deformation to create the illusion of a device being deformed. Let's look at it in more detail. So if you apply some torque to a compliant object using your two hands, it will bend like this, right? That makes sense. And let's look at the deformation from the side. So the torque is applied and it deforms like this, right? And yeah, let's see it again. So if you exert some multi-dimensional torque, like this one on the left side, the object deforms in the same direction by the twist angle of theta. So by the Hooke's law, we can know that the angle of twist is proportional to the torque we are applying to the object. So the torque is a tau here, and K is a spring constant. So basically, if we can estimate how much deformation will be made if we are applying some amount of force or torque on an object, and if we know that the spring constant of the object. And there will be some grain vibrations caused by this movement, and we simulate the vibration. So here it shows the torque, two-dimensional torque, and we use a feedback threshold that determines how much amount of force or torque changes are needed to cause a single grain vibration. So if you're applying some torque to an object, you'll see that torque cursor. And each time each time the torque is exceeding the threshold, it is playing a single grain vibration. So this is really slow. I just want it to be more clear. When it's really used, it becomes like this. So imagine you are bending a stick and you are feeling this kind of vibration. Like this. So the threshold is very large in this animation, but by making this threshold smaller, we can make users feel that there was a larger movement or there was more deformation for the same amount of force or torque. So, like this. In this case, they feel the object is softer. And if you increase the threshold, people feel that there was less movement for the same amount of force. So they feel that it is stiffer. So we can simply change the deformation stiffness by changing this threshold. And it is not just the stiffness, we can also control its maximum deformation range. So we can set a virtual stopping point like this. So when the movement reaches this point, it stops playing the feedback. Therefore, people feel like the device does not bend or deform or twist anymore, even they exert stronger forces. And we also used a different vibration to create the hitting the bottom feedback when you're crossing this stopping point. And while I've shown an example of a 2D deformation, same method can be used for 1D forces as well. Like the stretching force. You can just remove one dimension there, and the same algorithm just works for that. And you can also set the maximum deformation here. And we implemented a prototype device to test its feasibility. So the device is pretty simple. We built the device using an ATI Nano 25 6 degrees freedom force torque sensor, and a actuator, vibrotactile actuator, and two 3D printed handles. Assembly is very simple. You just screw the handles to the sensor, and you put the vibrotactile actuator in the handle, and voila, we have the Haptic device here. So to give you some numbers, weight of this device is around 140 grams, which is similar to the weight of an iPhone 8 device. The sensor is connected to the PC using Ethernet connection, and the vibration signal is generated by a tinge board through its digital analog converter. And the total loop takes less than 5 milliseconds here. And these graphs show signals used for generating grain vibrations and bottom-out vibrations. Grain signal is a 205 hertz sine wave that decays to zero. And the bottom-out signal is a 100 hertz square wave that is 20 milliseconds long. So, to identify the characteristics of the feedback or the illusion, we conducted a series of psychophysical experiments. We ran 3 psychophysical experiments to answer those 3 questions. First, do people perceive the rigid device as deforming without feedback? And second, can they discriminate different stiffness? And the third, can they tell differences between deformation ranges? So to run the study, we recruited 12 participants, and during the study, participants were wearing noise-canceling headphones, and they used the device in a box with their 2 hands so that they're not really seeing the device with their eyes. In the box was covered with black fabric, and to maintain the hand grasping positions throughout the experiment, we asked them to use 3-button foot pedals instead of using their fingers or hands to select answers. In the first experiment, we ran an absolute threshold estimation test, which estimates if people can feel it like bending, and if it does, from which stiffness level they start to feel the stiffness. So participants tried a sample and answered if it bends or stretches or twists, and the method increases or decreases the stiffness level until the participants start to not feel or start to feel the deformation. And this is the result. So none of the participants felt the device was deforming when the stiffness was infinite, which is, there was no deforming feedback at all. And there was a variation in where they start to feel it like deforming, but all participants felt the device was deforming when the threshold was smaller than 8 newtons for stretching, 0.125 Newton meter for bending, and 0.03 Newton meter for twisting. In the second experiment, we used a 2-down, 1-up staircase method with 2 alternate forced choice. So participants were asked to try 2 samples and select one that is stiffer. Stiffness differences between the 2 samples increased its difference. So the difference increased if the participant chose the wrong answer, and the difference decreases if the participant makes 2 right choices. So the session ends when it converges. So you can tell what is the amount of difference. People can tell the difference between those 2 samples. And here's the result. On average, participants could discriminate between samples with different stiffnesses when the difference was larger than 114% for stretching, 161.7% for bending, and 153.3% of difference for twisting. So they could tell the difference between those 2 samples with different stiffnesses, but the Jaeyeon D was higher than the physical counterparts. In the third experiment, we tested 5 different deformation ranges. So participants tried a sample, and they were asked to reproduce the amount of deformation they felt when they were trying the sample, when the device stops moving. So they reproduced the amount of deformation using the measuring devices we built. And this is a brief result. Actually, this graph shows the maximum perceived deformation range, which was perceived for the maximum grain vibration range. You can see here that individual differences were really, really large. So for the stretching, when we set the maximum deformation range to the largest, some participants felt that it was like 1.7 millimeters long, and some felt like it is like 15 millimeters of displacement. And for the bending and twisting, it is still very large. So some people thought that it's like 1.5 degrees of bending, some thought that it is 9 degrees, and for twisting, 10 to 46 degrees. So it's a really huge difference. But if we normalize for each participant, when we increase the maximum deformation range, actually the perceived length increase proportionally with the increase of the bottom-up threshold. So we could see that people can tell differences or can tell the changes of the movement range, but it may not be applied for different participants. So in summary, in this paper, we showed that Pseudo-Ben creates deforming illusions using a force sensor and a vibrotactile actuator. And I have to tell you that this is different from other haptic feedback technologies. This is a passive manner haptic feedback. So unless you apply some force to the device, you can't feel a thing. So it doesn't do anything unless you exert some torque or force. And Pseudo-Ben can simulate different stiffness and deformation ranges. but it may vary a lot across users. And we made the Pseudo-Ben 3D models, schematics, and code as open source. So it is all online. So I hope you build yours and use for your group projects. And that's the end of my talk. Thanks a lot for your attention.
Time for questions? And we've got a few.
Thank you. So I'm from Monash University. Thanks for the talk. Very, very interesting. I would have a question regarding the intensity of the vibration that you used. Mm-hmm. Was it always constant, or did you change?
It was always constant. So we didn't change any of the vibrations or vibration frequencies. It is all the same vibration. We just changed the thresholds that the vibration grain is being played.
Yeah. And did you try it? Did you try to change it, even if it's not in the paper?
That's actually a very good question. So previous literature showed that the vibration frequency doesn't really have an effect of texture. But if you modulate the vibration amplitude, it is actually it is actually affecting the texture of this movement, virtual movement. So if you make the amplitude to be more irregular, you feel that the surface is more rough. And we didn't apply that here in our project. But yeah, that is definitely something that you can apply to your project and see how it works.
Thank you.
There's one at the front here.
Hi, thank you. I was wondering if you could comment on the effect of friction between the user's hands and the handle, and then the choice of using a 3D printed material as how that affect the texture or the haptic illusion.
So can you repeat the question again?
Yeah, the first part is how does the friction between the user's hand and the handle, so if I have really sweaty hands during the experiment, will that affect the illusion of bending or stretching? And also the choice of using a 3D printed material for the handle versus a more compliant object.
Yep, that's a good question. So we don't know about that, but definitely there were some participants who mentioned that when I was trying these samples too many times and my hand got slippery, then it was more difficult to maintain the same location, especially if you're stretching the handles. So definitely that's something to think about. We didn't really consider for our experiments, and there was no actual slipping happening in our experiments. But I definitely think that the amount of normal force to keep the location probably varied by the friction coefficient between your fingers and the handle, and they may have different effects. But that's a really good point. Thanks.
Any further questions? Oh, there's one at the back.
Hi, very interesting talk. I was wondering if you looked at compression as well, rather than just stretching.
Excuse me, can you...
Oh, sorry. If you looked at compressing the tool, rather than just extending it.
Right. So our sensor is 6-degree freedom sensor, and we can definitely feel those contraction movement. And we didn't use for our experiment. We just wanted to see the one-dimensional movement and the effect of the vibrotactile feedback. But that is something that we may want to look at in the future. Maybe the direction may have an effect on how people perceive those movements. Yep. Thank you.
All right. Thanks.